Hello everyone. In this session, we will be discussing about how multiplication is going to be performed. Uh, so, Arithmetic for computers under the topic arithmetic for computers, we have been discussing addition subtraction. We have just seen the hardware for addition subtraction and how we are going to perform with the help of the available hardware infrastructure, and we have also discussed the flowchart. So, in this class, we will be discussing about the process of multiplication. So, the outline of this discussion will be we will just see how to manually multiply the two numbers in binary, and then we will discuss the hardware setup required for doing this multiplication, and the flowchart or the algorithm which is available, that is what we will be implementing in the arithmetic and logic unit to perform the multiplication operation, and then the trace of this algorithm that will also be discussed. Okay, so I've given the outline for our today's discussion. Now we will just proceed with the manual multiplication. Okay, now we are just going to see how we are going to multiply two numbers in binary. So binary multiplication, how it is going to be done. So let us take an example as given in this workout. So we are just going to take two numbers 11 and then 13, and the example what we are going to discuss is only of unsigned multiplication. So to start with, we will just discuss about unsigned multiplication. Okay, so we have to multiply plus 11 and then plus 13. Okay, so if you just see the product will be, it will be 1 3 is 3, 33, 1 1 is 1, 1 1 is 1. So the answer, the decimal product will be 143. Okay, so we are going to multiply this. So how we are going to do this multiplication in form of binary? So we have to represent the number. As you all know, positive number, it can be represented in the normal form. So 0 will be there for the sign, and of course, we are going to see only unsigned. So in case of unsigned, all the numbers are going to be treated as a positive number. So don't worry about the sign bit. You just take the magnitude alone. So the magnitude of 11 in binary, it is going to be 1011. Okay. So how we are converting this binary? So maybe you can take 248421 code. So I want to find the binary equivalent of 11. So 8 plus 10 plus 11. So this will be 0. So if we add this weightage, 8 plus 2, 10 plus 1, 11. So the 11 equivalent will be this one, and then 13. 13 is 8 plus 4 plus 12, 12 plus 1, 13. Okay, so this is going to be my 13 binary equivalent. So I have written plus 1 in binary like this, and now plus 13. Of course, sign bit is not going to be considered. We are just working out only unsigned multiplication. So you take 1101. So how we are going to do this multiplication? So in this, as we all know, the first operand is going to be referred as multiplicand, and the second operand is going to be referred as multiplier. I am going to multiply multiplier with multiplicand. For this, what is the manual procedure? So you will be examining the multiplier bit one by one. If the bit is 1, you copy the multiplicand as such. If the bit is 0, the partial product is going to be 0. So if it is 1, I will just copy the multiplicand as such. So it is going to be 1011. Okay, and of course, when you are doing this addition, what we have to do? So this is going to be an n bit number, and this is going to be another n bit number, and I think in the addition subtraction we have forgot to discuss this point. If we add two n bit numbers, okay, if we have two n bit numbers, if we perform addition, then the result can exceed to one more bit extra. So the result could be of n plus 1 bit. And similarly for subtraction, if I take n bit number and another n bit number, if I subtract, obviously the answer will be always n bit. So there will not be any overflow. But in addition, there could be an overflow. So the length of this bit could be n plus 1. Now if I take multiplication, if I take two n bit numbers, if I multiply, then the product whatever we are going to get, it may be of 2n bits in length. So this is going to be the general observation. So adding two n bit numbers will give n plus 1 bit sum. Okay, this n plus 1 bit because of overflow, and if I subtract two n bit numbers, there will not be any overflow, so the sum will the output also will be an n bit number. But if I multiply two n bit numbers, the product will be the double the length of the given operand, so it will be 2n bit. Okay, now so if we say 2n bit, it is not initially 4 bit, so this is going to be called as a partial product. It is not the final product, so this is going to be the partial product, which is referred as pp, and it has to be represented only as 8 bit. So I have to extend this 4 bit, and I have to make it as 8 bit. So when I extend this as an 8 bit, obviously we have to extend it only with the sign bit. The sign bit is 0 4 5 6, 7, 8. So 8-bit answer I have to write. Okay. Then you examine the next bit. So if this bit is 0, then the partial product is going to be 0. And after writing down all the partial products, you are going to find the sum. Okay. So if the partial product is 0, then you can omit this step. So you need not you need not write the partial product. And whenever you're writing the partial product, you have to write the partial product in the same position as the bit lies. Okay. For the first partial product, you have to start writing from the first bit. The second partial product, you have to write from the second bit. So the second partial product is 0. So I'm not going to write here. Okay. So this partial product is not going to be written. Now I will examine the third bit. So for the third bit, again the partial product has to be written only from the third bit position, and it is 1. So you will copy the multiplier as such. So this will be 1, 1, 0, 1. Okay, then you fill it up with zeros of the unused bit. Of course, this is going to be the third partial product. So I will start from the third bit. So these two bits I can make it as 0. Okay, this is going to be partial product 1, and PP2 is 0. So I have ignored that writing PP2. Then I am writing PP3. Okay. And then I have to examine the fourth bit. So this bit is also 1. So when I do the multiplication, again I have to copy the multiplicand as such. So this is in the fourth bit position. So from this position I have to start writing. So this will be 1, 1, then 0, then 1, okay, then 0. And here the unused bits, I think I can fill it up with zeros. So whenever we have unused bits, you can fill it up with zeros. So when I do this manual multiplication, I have to examine the multiplier bit. If the bit is 1, copy the multiplicand, and because we know the answer will be in double the length, so if it is 4 bit, you write it as an 8-bit answer. So the unused bits will be filled up with 0. So of course we are just discussing only unsigned, so it is going to be only 0. Having written all the partial products, now to find the final product, what you have to do, you have to find the sum of these individual partial products. So what is the sum of the individual products? Now it is going to be 1, 1, okay, 1. And when you add, see, you have to add. So whenever you are doing this addition, you do the addition with the decimal count. Then when you write the answer, you convert into binary. Here it is 1 plus 1 2, 2 plus 1 3. So what we have to do? So we have to convert binary 3 into binary. So you'll be getting 1 1. So you will write this 1 here. Take the 1 into the next bit position. So this is going to be the carry which you are going to take to the next bit position. So 1 plus 1 it is 2. So you will be writing it as 1 0. So 0, then 1 will be taken to the next bit position. 1 plus 1 2, 1 0 0 1. Okay. Then again 1 plus 1 2, 1 0 0 1. So you will be getting the answer like this. So the answer will be 1 0 0 0 4 ones. Now we have to find the decimal equivalent of this number to verify whether it is going to be 143. Okay. So how you will do? You will be assigning the weightage. So this is 2 power 0. So that is it is 1. 2 power 1 it is 2. 2 power 2 it is 4. 2 power 3 is 8. Okay. And then 2 power 0, 2 power 1, 2, 3, 4, 5, 6, 7. So this is so 2 power 7 is 128. Okay. So you have to add all these numbers. So if you add all these numbers, you check whether you are getting the final answer. So 8 plus 4 12, 12 plus 2 14 plus 15. So 128 plus 15. So you will be getting 8 plus 5 13, 3 1 4 143. So the answer expected is 143, and you have also got the same answer. This is how we have to do the manual binary multiplication. So the given number you have to represent the magnitude, and it is a array magnitude takes n bits. So here plus 11 occupies 4 bits, plus 13 occupies 4 bits. So the partial product every time you have to write it as 8 bits. When you are converting into 8 bits, the sign bit has to be extended. But here the sign is going to be 0, so you are going to extend only the 0th bit. So after examining the one bit, then you have to move on to the next bit. So bit by bit in the multiplier you are going to examine, and then you are going to write the partial product. As many number of ones in the multiplier, that many partial products you will be having. Whenever you are writing the partial products, you have to remember that it has to be written starting from the same bit position as that of that multiplier. So if I am examining the third multiplier bit, then the partial product for this bit has to be written from the same bit position. So the leftover bits will be filled up with zeros. Having done this partial product, then you have to keep adding. And when you are adding, if you get a decimal number, convert that into binary, write down the carry here, and then take the remaining bits to the next bit position. So like this, you have to do the addition. So this is how we are going to do multiplication. And now we will just see how we can implement that with the help of this hardware. So what is the hardware required for performing this multiplication? Okay. Now we will just see that. So if you observe here, So this is the block diagram that is going to help you to explain the setup required for multiplication. In this block diagram, we are just going to deal with two operands. So one is the multiplicand. So you will always store the multiplicand in the register M, named as M, and it is n bit register. So you will be referring the bits position as M0 to M minus 1. So it is going to be an n bit operand. So that n bit operand will be stored in the register M. Okay. And coming to this multiplier, I am going to store the multiplier in the register Q, and it is referred as Q0 to Qn minus 1. Okay, so totally n bit numbers. So multiplier is going to be stored here, and multiplicand is going to be stored here. So this is going to be an n bit number, and this is going to be an n bit number. So if I multiply two n bit numbers, as I already told, the product could become 2n bit. Okay, so since the product can become 2n bits, I need one more register. So I have a register which is referred as accumulator as an n bit number, n bit register. So this n bit register accumulator, to start with, it will be initialized with zeros because we don't have anything here. So as said, before starting the multiplication, we are going to initialize this M register with a multiplicand, multiplier in the Q register, and we are going to implement this multiplication as repeated addition. We are going to get the partial product and we are going to add it. Okay. So for that purpose, we need an n bit adder. So for this n bit adder, we will be feeding the multiplicand and the multiplier. Okay. Now if you just see here the multiplier, what is the multiplier? The multiplier is in AQ. So the multiplicand will be stored in the register M, and the multiplier along with the accumulator content, which is initialized to 0, will be now considered. So A will be 0 and you will be having the multiplier in Q register. Now what we are going to do, we are going to examine the LSB. So every bit you will be examining. If the bit is 1, then you shift and then activate the add control logic. So what will happen? It will start adding. So what it will add, the multiplicand will be added with 0. So the first partial product will be obtained and the answer will be available in accumulator. Then after doing this, then what we have to do, so you have to examine the second bit. So to examine the second bit, this bit has to be shifted out. So for that purpose, you are shifting right. When you shift right, the LSB will go out, and then the first bit will come to this position. And again you will examine. If it is 1, again do the addition. If it is 0, no need to do it. No need to add. Simply shift. So every time you are going to examine the multiplier bit by bit, one by one. If it is 1, you do the addition. If it is 0, don't do the addition. But after completing this, every time you have to shift this register. So if the answer is going to exceed 8 bits, so initially it will be n bit, and then if it is going to exceed 8 bits, the excess bits will be accumulated in this multiplier. So in the multiplier, we will be getting bit one by one outside. So every time you will be doing the shift right operation, and after doing this addition, if there is any carry here, that excess carry also will be considered when we are doing the shift right. So the shift right is going to happen along with this carry flip flop also. So the carry, this register and this register will contain the entire multiplication. So now we have discussed the hardware required to perform the multiplication. As I told, we have to deal with two operands. One operand is multiplicand M, which is stored in this M register. Another operand is multiplier Q, which is stored in this multiplier is stored in the Q register, and the final product could be in 2n bit length. So we are using one more extra register called accumulator. Initially it is initialized with 0, and the partial product will be accumulated only in this AQ register. So every time AQ register will be having the partial product. Okay. So we are examining the multiplier bit one by one. When the bit is 1, you give add control, so it will perform this addition. And then after doing this, you shift this bit right, so it will go out. The next bit will come, and you check that next bit. If it is going to be 0, then no need to do addition. So what we have to do, simply you have to do the shift right. That's what we have done here. So we are just including two zeros here because the 0 addition is not going to change the result. And when it comes for the next multiplier, again you will be examining. Like this, you are going to examine all the bits in the multiplier. At the end of the multiplication, all the multiplier bits will be shifted out, and the product will be available in A, and whatever the bit coming in excess, that will be made available in Q. So the final answer will be available in AQ. So this completes the discussion of the manual multiplication procedure and the hardware details. Now we will see how this algorithm is going to be implemented and how we can trace the value.